This is a Clos network. It is a Clos network denoted with the following representation. Okay, it is a 3-3-4 Clos network. Okay. 3-3-4. And in general, a Clos network is represented by three numbers, or specified by three numbers: n, m, and r. These are all positive integers. Okay. And each input switch is n by m, and there are r of them. Each output switch by symmetry is m by n, and there are also r of them. And each middle switch is, of course, by dimensionality, r by r. And there are m of them. So if you give me three numbers, I can then draw a Clos network. Now, no wonder in this specific case, we have 3-3-4. Each input and output switch is 3 by 3, and there are four of them. Each middle switch is 4 by 4, and there are three of them. Okay. Now, what about the connectivity pattern among these small switches? Basically, each of the output port from each input switch is connected to each of the middle switches. And that's why there are M of these middle switches, because you need one for each output port of each input switch. Okay. And that is why each of these middle switches is R by R, because you need all of them in order to face all of these input switches. And then it's exactly symmetrical on the side facing the output. So this is a very dense connection. Now, of course, it's not full mesh, okay? I'm not connecting every switch with every other switch. For example, input-output switch are not directly connected. But it is staged, okay? It is a multi-staged dense connectivity with a lot of rich connectivity patterns. And of course, in this case, it is a three-stage Clos network. You can have actually any odd number. Okay, now 1 would be too much of a trivial case. Otherwise, you can have 5-stage, for example, 7, 9 stages. In fact, in the example coming up, we'll see recursive expanding a Clos network. By adding more stages, you can reduce the size of each stage switch. So that's the trade-off. Again, back to this example, we got a 3-stage 3-3-4 Clos network. And in general, you can have a 3-stage NMR and then recursively expand that so that it starts to use smaller and smaller switches. This is such a rich connectivity pattern that has become a very useful tool in all kinds of study around interconnection network. For example, what kind of condition can guarantee non-blocking properties in a Clos network? Okay. Well, if you think about it, okay, without showing you the answer first, what we really need is basically that there are enough middle switches, and there are M of them. So we need M to be big enough. Okay. We need M to be big enough compared to basically the number of inputs that can be supported per switch, or by symmetry, the number of outputs that can be supported by each output switch. So we want M to be sufficiently big. Okay, M should be bigger than some kind of function of N. It turns out that there's a very simple answer. M is to be greater than or equal to 2n minus 1, a simple relationship. In fact, it is perhaps more instructive to write down this 2n minus 1 as 2 times n minus 1 plus 1. Now, of course, algebraically, these two expressions are the same. But this is actually the logic, the reasoning behind the derivation of this simplified answer here. Let's look at an example. This is a little weird Clos network, but it suffices to illustrate the point with a very small graph. So this is a graph of a three-stage interconnection network following Clos topology. You've got on the input side 2 switches, each is 2 by 3. Okay. On the output side is 3 by 2, and therefore there are 3 input middle switches, each of which is 2 by 2. Okay. So now what we want to do is to say that if I configure this Clos network in a certain way, denoted by the blue lines already, and then there's a new incoming traffic, how can I make sure that I can connect that new incoming traffic from its input port to the output port? Okay, so again, the terminology, these are the ports, these are the input ports, these are the output ports. This is a switch, so they are of the input stage switch. Okay, this is the input port, output port, input port, output port. Okay, so they are the input and output ports of the middle stage switch. And same thing on the output stage switch too. The blue line shows a particular configuration already. For example, suppose there is a traffic that arrives on input, this input port. Okay. Altogether, we've got 4 input ports, which we can label them as 1, 2, 3, 4, or following binary number notation 0, 1, 2, 3. Okay, let's say 0, 1, 2, 3. So it arrives at input port 1, and let's say its intention is to go to output port 0. So how can I go from here to there through this maze? Well, one possibility is I can connect it by connecting input port 1, or the lower input port, to the middle output port of this input switch A. Okay, and then since it's connected to the middle output port of switch A, it's going to naturally go into the middle switch at the middle layer, at the middle stage. Okay, and now it needs to go to this output port, and therefore needs to first arrive at this output switch. And the way to arrive at this output switch is, there's only one way, which is to connect over here. Okay, instead of going down. That would be going to the wrong switch. So it goes to the correct output stage switch, and now I just need to get to the correct output port. And that is accomplished by connecting this way. Okay, so now you see this connectivity. And then similarly, there are 2 other existing end-to-end traffic already established from this input port going to this output port. Okay, and the way is to first connect it this way on the input side, and then it naturally leads to this middle switch, the top one. You connect it doing a cross, and that will give you to the correct output switch. Do another cross, this gives you the correct output port. Same story over here. Okay, in fact, you see that the total input port counted from 0 to 3 basically shows this pattern. You go from 1 to the output port, which is 0. You go from 2 to 1. You go from 3 to 2. This is called a permutation. If you write them in binary notation, you will see. But that's not the point here. The point is now there's a new arrival. Okay, arriving at a vacant input port. If they're all taken, then there can be no arrival, so there's no problem. But there is a vacant input port, and there is a vacant output port. And this arrival exactly wants to go from this vacant input to that vacant output, from input port 0 to output port 3. So how do I go from here to here? Well, I can actually have a choice, right? I can, for example, go from here over here, and then that will lead to me here, and then I can go down this way, and then I can go down this way, right? Now, our point is not to show, hey, I can solve this puzzle. This puzzle is too easy to solve. The point is to now illustrate a common thread, and that is when all the other input ports are already occupied, okay, and there are basically n-1 of them, okay, at this switch, and all the output ports, all the other output ports are occupied at this at the other switch. Okay, that's another n minus 1. These n minus 1, in this case is only 1 because n is 2, could have gone through, must have gone through some middle switches. Okay, same thing here. And they could have gone to different input middle stage switches. Indeed, in this case, this one have gone through this middle stage switch, this has gone through this middle stage switch. Okay, so both switch B and C in the middle stage are occupied. Right? And you could have an input pattern where in order to reach from this to that point, you cannot reuse any of these existing middle stage switch. You have to use another one. What if you don't have another one? Then you may be stuck. You may be blocked. But if you do have another middle switch, then you will always have degree of freedom to be non-blocking. And that is to say, if we have already got 2 times n minus 1, meaning n minus 1 from the input ports of the input switch shared with this new traffic, same thing for the output, they all go through different middle switches. So you already got 2 times n minus 1 bracket middle switches. All you need is to have just one more middle switch and you'll be okay with non-blocking. And that is where we get this lower bound. 2 times n minus 1 bracket plus 1, which simplifies to 2n minus 1. If you have that many middle stage switches, if your M in Clos network specification is at least as big as this number, then you have non-blocking. Okay. Now, a couple of remarks. First of all, say M greater than or equal to 2n minus 1 for non-blocking. Where is R? Right? I know that for the entire Clos network, there are basically n times R number of input ports total and n times R output ports total. So if I want to really build a Clos network to take in a lot and connect to a lot on the output side, if n cannot be too big, okay, because n must be small enough so that 2n minus 1 is smaller than m. If n cannot be too big, maybe R can be big. And indeed, there's nothing that prevents you from running really big R. You can make R 1,000, okay? But then the problem with that, as you can see, is that you're going to have really big middle switches. Okay? Because the middle switches are R by R. So, true, you can make R really big, but then you've got really big R by R middle switches. Maybe you can do something about it. And indeed, in a minute, we'll see how we can recursively expand the middle switch into, in turn, multi-stage switch network. So we can recursively apply Clos network ideas and in order to tackle this large R by R middle switch. So that's question number 1, right? Question number 2 is, this is for non-blocking. What about rearrangeably non-blocking? We should have a looser condition. M doesn't have to be as big as 2n minus 1 anymore. And indeed, as long as m is bigger than or equal to n, okay, this is almost basically a half of reduction in the how stringent this condition need to be. Okay, as long as m is bigger than or equal to n, as long as there are as many input middle stage switches as the number of input ports per input switch, then Clos network is rearrangeably non-blocking. And the way to prove this is through a constructive algorithm in the homework problem. Now, there are also many different combinations. For example, you can first build a tree, and then you can hook into a Clos network to the point where you can build a large enough switch. For example, 128 by 128 or something. Then, well, build it. And then when say, I can't do it anymore, then don't build bigger switches connected into Clos network. This is one of the commonly used architecture in cloud called a virtual layer 2, okay, VL2, recently developed. And there are many other alternatives, variants and alternatives. Clos network is not the only kind of topology you can have for interconnection network. In the advanced material part, we will say a few more words about those. Now let's run through a particular example of building and then expanding and rearranging and then folding a Clos network. Let's start with a 3-stage Clos network. Okay, suppose we want to build eventually 8 by 8. Okay, and we only want to use small 2 by 2 switches. Okay, so how do we do that? Well, here's one starting point. Let's build a Clos network where N is 2, M is 2, and R is 4. So you got 2 by 2 switches on the input, 2 by 2 on the output. There are 4 of them, so that you get 8 total input-output ports. And therefore, that means each input middle switch is actually 4 by 4. And there are 2 of them. Okay, that's fine. You provide all the connectivity possible between input and middle switch, and then between middle and output switches. This is the Clos network, and you can just stop here. You can say, that's it, that's my answer. But suppose you say, I don't want to build a 4 by 4. Okay, actually, of course, in practice, 4 by 4 is still fine, but our numerical example will have to be small, and therefore, let's say 4 by 4 is too big already, and we want to replace it by 2 by 2. So how can we replace it with a bunch of 2 by 2s? Well, we can recursively apply the idea of Clos network. Let's now build a 3-stage Clos network. Okay, that is actually 2, 2, 2. So each input is 2 by 2, each output switch is 2 by 2, and the middle one is also 2 by 2. And then you get the full mesh connectivity between input and middle, and between middle and output stage switches. Now you got 6 2 by 2 switches to get one 4 by 4 switch functionality. So you're going to substitute this thing, okay, back into each of these 2 middle stage switches, and this is what you get. Okay, you just substitute this collection of 6 2 by 2 switches as one 4 by 4 switch into the original. So this is a combination of one Clos network here with another Clos network, a composition of 2 Clos networks. And now you get the gist that I can keep recursively expanding from 3 to 5 stage, 5 to 7, 7 to 9 stages to make the middle stage small. Okay, so now we got a 5-stage composed by 2 3-stage Clos networks. And now everything is 2 by 2. 2 by 2, 2 by 2, and so on. And you can see the connectivity pattern is quite rich, right? Within each of this inner loop Clos network and in the outer loop too. Now we can also stop here, but we're going to do a little transformation by rearranging appropriately the position of the switches in stage 2 and stage 4. Okay. Now we can just use input, middle, and output stages because there are 5 stages now. Stages 1, 2, 3, 4, 5. If we rearrange the stages 2, 4 switches a little bit, we receive the following pattern. Okay, so basically what we do is to move this up and move this down. Then we have the following connectivity pattern. And now we'll do the last step, which is folding. We're going to do folding to say that, you know what, so far we assume up to this point that all these links are directional links. They flow from left to right, from input to output, right? So all these are directional. Now, what if these links actually bidirectional? Then, by symmetry around the middle or the stage 3 switches, you can see that, hey, the left-hand side and the right-hand side are mirror images of each other, right? The connectivity pattern, you can fold them. In fact, if you really cut this out on a piece of paper, you can fold it exactly, literally, in the middle. Okay, you can put this part, it's going to be hard to illustrate this 3-dimensional operation, fold it over here. Okay. then what you end up with is actually something simpler. You basically delete this part, and you make all these links bidirectional. Okay, all these links bidirectional. Then you actually get back to 3 stages. Because whatever goes out here, you can just view that as the folded version, except the arrows, instead of pointing from left to right, would be pointing from right to left. Now that is the final simplified version that we have. This becomes a network with 12 2x2 switches, making altogether a 1 8x8 switches. And we call this folded Clos network, so-called fat tree. Not to be confused by the use of the terminology tree. Fat tree is not a tree. It can achieve what a tree cannot achieve. Fat tree is just a folded Clos multi-stage interconnection network.